So here we go. First I have here the definition of electric potential energy, which is just the potential energy a charged particle has due to an electric field. So we're not going to necessarily dive into electric field so much today, but we all know what an electric field is. It's an area of influence around a charged particle where a particle would feel some force due to that other charged particle. So the argument we make here is we're going to say that the change in potential energy is equal to the work done. Now, we all know the argument about work done to versus against the field, so we're going to later get this negative, but we're going to kind of explain that away in terms of this negative, based on the way we're setting the question up, is the work done against the field. And what we're really looking for is the work done by the field, which would just be the negation of that. So when you look up this formula in the reference table, it gives you positive instead of negative, but we'll get there. Okay, so what we're going to do is we're going to say the change in potential energy is equal to the work done. We can also make the argument that that's equal to negative change in kinetic energy, but I digress. We don't have to worry about that right now. Okay, it's also, so work is equal to the integral from R1 to R2 of the force F of R dr. Okay, so now we come over here and we're going to say the change in U is equal to, from R1 to R2 of the force, which would be electrostatic force, dr. Now, you do that integral, you end up with negative KQQ over R. You do it from R1 to R2, and what I write here is if you allow one of your bounds to be a relative 0 point, so just like we did when we did dropping things in gravity, whereas the floor isn't technically zero potential energy, we allowed that to be our relative 0 point. So we're doing the same thing here. If we allow one, either the beginning point or the end point, to be our relative 0, we can then get rid of one of these, and that leaves us with this formula here, which is KQQ over R. So this is a change in potential energy, which is equal to positive change in kinetic energy, which we kind of talked about before. Now, what I wrote here is I'm trying to build up these formulas in the way that they're on the reference table. So this goes back to Regents physics. We have V equals W over Q, work over charge. So V is then equal to UE, work and energy, work and potential energy being the same thing, over Q. So we can then write that the UE, or the electric potential energy, is equal to V times Q. Now, you see that on your reference table, they write UE equals Q times V, which I just said, and they also write this, which without the negative, because I told you before, it's a matter of work done by the field versus against the field. And I just leave in this reminder here. Note that K, the 1 over 4 pi epsilon sub 0, is K, and K is actually numerically that value. So, whereas this is what they write, you can write this as K, which is the way we formulated it before, KQQ over R squared. Okay. Now, what we have here is I have a charged particle creating an electric field. And what we're going to talk about is we're going to talk about the electric potential at that location. So I'm going to place a little charged particle, a little test charged particle here. Okay. Now, starting off with V equals U over Q again, we're going to look at this a little bit differently. We're going to say V equals KQQ over R, which is the formula we just came up with before for electric potential energy, divided by Q test. Now, why is that the case? Well, because if that's the particle we're placing here, we're looking for the electric potential energy between the particle causing, so Q sub C is what I'm using for causing the electric field, and Q test, which is a charged particle that is being used as a test particle, over R, which would be the distance between these guys, divided by Q test. The Q test goes away, and we end up with this guy, which is a very powerful formula, because that's saying that the electric potential in any location is based on just the distance between the location and the particle causing it, the charge of the particle causing it, and K. Now, if we look at a situation like this where now we have three separate charges, well, you see here it says the net V at the point P would just be the sum of the V from each of the different charges. So I also gave you a huge reminder here because this is super duper important. Remembering that electric potential and ultimately electric potential energy are scalar values. Energy is a scalar, so you don't do a free body diagram. So what you would do here is you would just say K Q1 R1 plus K Q2 R2 1, 2 plus K Q3 R3, so on and so forth. You could factor out the K. Then you have K Q1 over R1 plus Q2 over R2 plus Q3 over R3, etc., etc. Now, if I come back over here, nope, hold on. If I come here and I look at this formula, this is exactly what I just wrote there. This is V, remember 4 pi epsilon sub 0 is K, and then it just says the sum of all the Q's and all the R's. So this would be, in that particular case I just showed you, Q1 over R1 plus Q2 over R2 plus Q3 over R3, so on and so forth. It could be 10, 100, 1,000 of these things. And eventually, if we were going to do an infinite number of these things, this would obviously become an interval, and we'll dive into that later in the week. All right, so let's just do a quick example. Again, I know we're running through this quick, but this is stuff that you all know already. It's just kind of a hopefully kick in the pants reminder of how to do this. So here I have a square with sides of D. I have a point X in the center. I have Q over here, 2Q here. And the question is simply, what's the electric potential at point X, so in the center? So I'm going to start with the formula. K Q1 over R1 plus Q2 over R2 plus Q3 over R3. Now, I'm going to take advantage of the symmetry of this thing a little bit. So I'm going to say V K. Now, we have a Q, and a 2Q. So if we want to call that 1, this 2, and this guy 3. Now, since we know the distance is the same, at least for now, I'm just going to write this as R and R and R, because that distance here, and that distance here, and that distance here are all the same distance. So, what do I end up with? I end up with K 4Q over R. Right, Q plus 2Q. So 4KQ over R. Now obviously I'm not just going to leave this as R. I'm going to put it in terms of D. So do you remember 4KQ over R. Now, remember that the diagonal rather of a square is just rad 2 that side. Half the diagonal is rad 2 over 2 the side of that square. So I'm going to come over here, 4KQ over rad 2 over 2 D. Now, I can flip and multiply that. So I'm going to get V equals 8KQ over rad 2D. Now, could you go further than this? Sure. Could you rationalize the denominator? Sure. Do I think you need to? I really don't. I can't imagine any teacher, AP grader, anybody who's going to not accept that answer. Okay? So, just going to go back to this, and we're going to do one more quick little exercise with this. So I'm going to clean it up. Now, I know we've done these before, but I just, again, want to remind you of how electric potential energy could play in here. So let's say I wanted to take and place a particle of charge Q, bring it from infinity to this location that we were talking about. And I wanted to find out, that wasn't Q, that was 2Q. And I just want to find out how much energy is required to do that, or how much work would be required to do that. All right, well, let's move this guy out of the way. Put him off, say he came from over here instead. Well, if I'm going to say that, I'm going to say my work is going to be equal to my change in potential energy, right? So it's going to be potential energy before the guy was there minus potential energy after he was there. So we go back and we label these 1, 2, 3. We'll call that location 4, or charge 4 once it's there. Beforehand, we had U of 1 on 2, U of 2 on 3, and U of 1 on 3. Now, afterwards, we have all of those guys still. Combined with all of these guys who are already here and their energy interaction with the new guy. So we have U 1 on 4, U of 2 on 4, and U of 3 on 4. So why is that important? Well, note the way I wrote this. If you look here, you have all these 3 guys minus, oh, that's right, all these 3 guys again. Da, da, da. And it turns out that the work required to put him here is just equal to this. Or you could say it's just equal to the potential energy between the new charge and the old ones. Okay, so I guess just to go through with this, let's go and do the calculation. So we got the work is going to be equal to K Q1 Q4 over R1 plus K Q2 Q4 over R2 plus K Q3 Q4 over R3. Okay, so we're going to factor out the K. We can ultimately factor out the R as well, because it's going to be the same again, remember, because it's just the distance between here and here, and here and here, and here and here. Okay, so we're going to factor out K. Factor out K and R. And then we're just left with, well, Q1 times Q4 plus Q2 times Q4 plus Q3 times Q4. So, let's see. Q1 was Q and Q4 was Q. So we got Q squared plus Q. Oh, hold on. Forgive me. 2Q times Q and Q times Q. So this guy is also Q squared. This guy is going to be 2Q squared. So we have a total of 4Q squared. Right? So we have K over R for Q squared. R we have to replace, so that's going to be the rad 2 over 2 D times 4 Q squared. We're going to flip and multiply, so now we have 2K for Q squared over rad 2D. And it looks very, very, very similar to what we had before. 8KQ squared over rad 2D. So, I do hope that helped. I hope that kind of, if nothing else, was just a reminder of everything we've done up until now. Oh, that guy looks a little sinister. Soften his eyes a little bit. Anyhow, so there's an assignment posted on the AP Classroom that kind of goes along with this stuff. It's just, I made it simple. It's just multiple choice. And again, I know that the AP exam isn't going to have multiple choice, but I also am mindful of the fact I asked you to do that other assignment, which, because you're looking at it in the two different aspects, both how to do it as well as how you would better choose to answer it, whether you'd like to type it or not. I know that that's a little bit cumbersome, so I'd kind of try to make this assignment a little bit easier for you. So again, I'll be posting this video. You'll have the questions to work on. You have that other set of questions to work on. Please make sure you're doing them. The AP exam is coming sooner than you think. It's in 3 weeks. 3 weeks from today, I believe. And we still have a whole bunch more of electricity to go over, and we have to recap. Now that we know the types of questions they're going to ask, we also have to go back and we have to do a little bit of mechanics. So we got stuff to do, all right? So let's not get lazy now. I know it's your senior year and all that stuff, but let's keep pushing through, all right? I will talk to you guys on Friday. I will be posting another one of these on Wednesday on electric fields and things, which I told you guys on Friday. And that's it, all right? So I'll talk to you soon.